Okay, here we go. All right, so what we got, could you guys decipher what this means? You're about to run out, I think. What is that? Can you guys, oh, you can't see it. What you should say is, that means you don't have a clue what you're doing, just be quiet. Oh, there you go. What that means. What does that mean at this moment?
What is the derivative of the function of
It's the
That
area,
would be f prime.
area of the points A to B to the x-axis.
Okay, that's beautiful. That's perfect. I'm sorry, I made it sound a little serious. So it's the area between the x-axis and the f function from A to B. That's what that means at the moment, right? In fact, I said the word integral, and that's fine. That is the integral of the function. That's what we call it. So the process of finding the area under a curve, we call it integration. At the moment, the only way we have to do this is by approximating it. And in fact, we use rectangles. One thing I thought might come up. So this, where did this come from? Let's go there. Do you remember where that came from?
That came from the summation of all the rectangles.
Okay. Somebody else help me out. So you're right, Sophia. So somebody else help me out. It's the adding up all the rectangles, but more specifically, why is it along S? Why did they decide that? Partially because they were most likely on some kind of drug, but why did they make it along S? What does that relate to? So the sum, but what kind of sum? So long S. So the infinite sum. Yes? So this process here we talked about. And all we do to get to this means the exact area. This is an approximate area, so I can make n 6, I can make n 10, I can make n 1 billion. No matter what I make it, it's going to be an approximate area. Because I'm using these imperfect rectangles with flat tops to estimate a curvy dude. The only way to possibly make it perfect is to ramp the resolution to infinity. And that would be this. So this, we chose this symbol to represent it. The nice thing is, how do I calculate this? Where does that come from? Yeah, b minus a over n. So we also incorporated that into that symbol. So that symbol does a lot of work. It has the infinite rectangles from A to B. All bam, right there, that one symbol. Delta x, of course, becomes dx because now it's an infinitesimal step. And xi just becomes x because I'm not just taking every ith input, I'm taking every possible input. So my rectangles are getting infinitesimally small. Okay. So everybody with me? So that's notation. So when you see this at the moment, you think this. So I can either estimate this, that's 5, 1, using like 6 rectangles, or I can go through that crazy ass thing we did where I had to tell you what the sum of I was, the sum of I squared. Are you guys all with me? Okay, let me stop for a moment. Is everybody really, really with me? And you're all like, why would I start now, Jeff? Okay. You guys don't want to talk to me. All right. So, let's try an example. I don't necessarily, unless, does anyone, okay. So I gave this handout out yesterday. Does anyone else still need this handout? Ah, okay. You were here, were you? No. Okay, so you didn't get your stuff back. Oh, you also, that's right.
Yeah.
Is everybody else good with,
I've been sleeping well.
did I leave one for myself? Oh, yeah.
Like 8 or 9.
So, this process here
Yeah.
is related to, in a way, the limit definition of derivatives. It's related to it in the fact that this is the real, behind the scenes, everything we ever do going forward with integration is actually this. We're just gonna develop shortcuts. Because I love math, but I don't wanna do this every damn time. Screw that shit. And that's the great thing about math, is we start to develop patterns, we turn those into shortcuts, and then we apply the shortcuts. But never forget, this is what an integral is. It's this. So, if you guys really, really want to, we could do another example of this. So yesterday, I think we finished this side, right? Yes. Another upside down parabola, because I am never-endingly creative. Okay. Are you guys, the answer to this is no, but if I say it like this, are you guys semi-confident in your ability to do a problem like this? If you have this sitting next to you. The steps, it's very formulaic. Who knew in mathematics, but it's a very step-by-step recipe. Yes? Okay. And again, the summation of I squared, I cubed, I'm going to give that to you. Right? And that's on the other side, I think, yes? These guys. Bam, bam, bam. Okay. So if nobody wants to do another example of this, which is very fine, we'll do something else. So what we're going to do today is start to make the connection between finding the area under a curve and the antiderivative. Okay. If any of you have taken calculus before, it's really easy to forget there's a connection that needs to be made. You just sort of assume it's the way things are. So let me set up a few things. Here's the trippy thing we're gonna do. We're about to create a function that we've never seen the likes of it before. One reason we've never seen the likes of it before is because integration itself is new, and it's gonna be based on integration. But even beyond that, it's gonna be a bit tricky. So let me just give it to you. Here we go. So write that down.
What section is this?
5.3, I believe. Yes. The name of this section shows you why I said earlier this is one of the most important. The name of this section is the Fundamental Theorem of Calculus. Damn. I affectionately refer to it as FTOC, FTOC. So there's going to be FTOC 1, FTOC, sure Jeff, FTOC 1 and FTOC 2. There's going to be two parts to this theorem. And the first part is nifty, the second part is insanely important, it's everything. The second part of FTOC is everything. Oh shit, who else is still? Is she over there still? Okay, good, okay. So, Bella, can you do me a huge favor? Can you go tell her real quick to stop and come over? Thank you. Okay. So help me out. Help me figure this out. What is it that's changing here? Can somebody just look at the integral? Tell me what am I finding the area from what to what?
Oh, the t from a to x.
From a to x. So what is it that somebody's allowed to come along and change?
X.
So I can change. So here's the idea. I have a function. It's what it sounds like. Okay, now the exceptionally tricky part of this is, do you notice why I have to now call it the t-axis? The input is t now, because x is the thing I can change. So it can't be the x-axis anymore, because x will be whatever somebody tells me it is. Somebody says it's 7, so then x must be 7. It can't be the entire axis. Yes?
Are the letters themselves a bit arbitrary, or do we choose T on purpose for time or something later?
All the letters we ever use is arbitrary. Within our choices, it is related to time,
Cool.
to a certain degree. It's more related to parametric. Do you guys remember parametric stuff from your pre-calc? No? All right, if you take me for Calc 2, if I ever teach it again, I use an Etch-a-Sketch to teach parametric. You guys know what an Etch-a-Sketch is? So I use an Etch-a-Sketch. I have an actual Etch-a-Sketch. I have a spirograph game too in my office, and I use them to teach certain things. Etch-a-Sketch is cool. I'll stop because that's not important. But T, we normally consider T to be the parameter. T is very often the behind-the-scenes controller of things. Very Illuminati. T. Okay, sorry. There it is. That's the good one. That was so funny. No. Okay. So, if somebody comes along and says, I want g of 3, well then I would go to 3 and I would figure out the area, and that would be g of 3. So the output to this function is an area. The area from A, and what is A? Whatever. It's just for any g function, it would be set to be 2 or 3 or whatever. We're going to find out later that it doesn't matter what it is. But it kind of seems like it should matter. So I go from A to 3, A to 4, A to 5. Somebody can just change x. So let me see if you guys are understanding this. What would g of A be? Yeah, why is g of A 0? If I put an A in, I'm finding the area from what to what? A to A. So what would the width be then? And if the area is width times height, the area is 0. Okay, cool. So here, let's do a problem like what's in the book. That would be great, Jeff. That would be really great, Jeff, if as a teacher you could really prep us. Okay, be quiet. Imaginary student talking to me. Let's do this. Look at that scale. That scale is perfect. Be quiet. Okay. So everybody see all that? Everything's supposed to be a whole number there, so if it looks like it isn't, it is. So leave me alone. Or an integer if you want to be all correct about it. So I'm going to define, in this case, I'm going to define my function. You can think of the g function as the area function. I'm going to define it as the interval from 1 to x. This is my f of t. So, I don't want you to say a word. I want you to figure out what g of 3 is. This is very easy, but at the same time, it's crazy hard because there's a lot of shit that we just went over that I'm just sort of slamming it, like, do it! The great thing about this right now is I'm never going to look at what you're doing right now. So do what you think you can. We said what g is. I told you just a second ago what is the function for. So that's all you need to find. You have to do it using calculus. No, you don't. Of course you don't. We talked about that before too. So can somebody, besides you two, can somebody tell me in English what g of 3 wants from me? Yeah, it just wants the area under the curve from 1 to 3, which you could further translate to the area of that first triangle. Yes? That's all that wants. You guys see that? I want to get the area between the x-axis and the function from 1 to 3. Well, that's just the area of the damn triangle. What is that?
3.
Yes, because it's 2 times, well, let's see. So this will be, how tall is it? 3 times 2 divided by 2 is 3. That's crazy science. So what about, what's g of 4 then? The one mistake students make with this is they say, well, it's just that upside down triangle. No, it isn't, because where do I start? Where does g always start? 1. So don't I already have the area from 1 to 3? So this now just says, okay, add to that from 3 to 4. Yes. Now what's trippy about 3 to 4 that we've talked about before? We have no
It's
trouble.
the negative area.
It's negative area. If this is a change in profit, we're happy, we're sad, but from 1 to 3 we made money. Now we are losing money. Yes? So my answer to G4 should be less than 3. I should be losing something. What is the area of that upside down triangle? Well, that's the name of the damn thing. The upside down? Start this one. What's, sorry?
Negative 1/2.
So this will be 3 plus, the width is 1, the height is 1, so it's negative 1/2. So that would be, you're not going to believe it, it's going to be 2.5. Are you guys understanding this? So there are problems in the homework that I believe are just like this, that merge the idea of all the integral wants is the area. If the shape it makes is a geometric shape, I don't need calculus to do it then. If the area makes is some curvy side, I don't have any freaking curvy sided geometry. Or let me say it like this, you don't have any curvy side geometry, so therefore we have to use calculus. Yes? Maybe? Are you guys doing it? So, sort of like if I asked you what's the derivative of 7x plus 3, you could do the limit definition, or you could just go, oh, I mean slope, and the slope is 7, it's 7. Do you see what I mean? Derivative is slope. If you can find the slope easy, do it that way. Integral is area. If you can find the area easy, do it that way. Maybe. Screw you, Jeff. Yeah, and again, it doesn't really. What would g of 1 be? 0, of course, because I want the area from 1 to 1, so that would be 0. And it's not 0 because it's there. It's 0 because I haven't moved it. Yes. Okay. So. Next step. What is this? Oh, good. Did she come back? She's not here yet. I'm gonna have to take a step away in a minute. Okay, here we go. So let's do this. I've got my g of x. I've got my little picture I can make. Oops. And it could be negative. I'm just doing this for the ease of what's going on. Good job, Jeff. Now let's say, okay, I'm gonna build this a different way than I normally do. I kinda like that. And my function keeps going, yes? That's my f of t, and it goes this way too. Okay. everybody agrees, you all agree, that even though this function is defined functionally, it's still just a function. And what calculus can we do to any function I give you? We could do a derivative, correct? So I want to do a derivative of this function. So I want to figure out what g prime of x is. Yeah, this is perfect. Can you guys, you're gonna love this. Limit definition of derivative. Can you write what that would be for g prime? Oh, great. Just the limit definition by itself. I think you guys are more than likely thinking I'm asking you to do more. All I want you to do here is g prime of x. How does it work? The limit as h goes to 0 of g of x plus h minus x all over h. That was nothing like pulling teeth. There was no similarity between them. Okay, right? And again, I understand. You guys probably like, well, this is all new. No, that's old shit. If I ever want to find the derivative of a function and I have no idea what it is, and it's not related to any other function, I have to go back to the limit definition. Why have we not used the limit definition very much in a while? Because I was able to build off of other derivatives that we knew. I could use chain rule product, well, I could do all that. I could use implicit, I could do all this shit. Yes, I didn't have to go back to limit. For this funky ass function is not related to any other function. I've got to go back. Well, like one of my professors, he was from Australia, he always go back to fundamentals, go back to fundamentals. I'm like, ugh. All right, but this is the fundamental. This is how I do derivative. So let's do this. Let me draw a better picture because that picture up there sucks. So here's A, here's X. Okay. Do you see on the top, I need G? So what does this represent right now? What does this represent? You can do it. What does that represent? Okay, beautiful. I love it. That's the area. What symbols directly represent that? Do it again? No. I appreciate that, but no. Based on the function we're using. So remember, what does g of x mean here? 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 Like you just said, it's the long ass s, which means,
Yes.
what's the long ass s mean? Area. From what to what? No. So in symbols, what is this? You gotta kick yourselves. This is g of x. That's all it is. You just told me, what does g of x mean? The area from a to x under f of t, yes? So that's g of x. How do I get g of x plus h? Go h further, yes. I love it. Just go a little just add h further, yes. So if I add this area in, now that becomes g of x plus h, yes? This is such a kick-ass, I don't know, I love you guys. I need you to let go. Just, g of x is weird, but what does it give me? The area between a and x, that's what it gives me. So when I draw a picture and I got a function, I go a to x, that's g of x. That's what it does, that's its job. Yes, this g's job is to give me the area from a to x. So then if I want g of x plus h, oh, I just go a little, just a little further. So like we did with g of 3 and g of 4. With how we get g of 4, we just went a little further. Yes? Okay, I love it, I love it. This is trippy. But again, you're never gonna have to do this yourself. If I have created a new function, what's one of the first things we do in calculus? What is that function's derivative? We have a new function, it's the area function. What is that function's derivative? Well, I know what I have to do symbolically. I know what I have to do. So what I'm doing right now is I'm tearing this stuff down so I can make sense of what the shit this is based on what I know g of x is. Yes? What the shit is g of x plus h minus g of x? If I could figure out what that is, I could simplify that damn thing and actually do something with it. Yes? Can I factor the top of that? Can you factor area? Not easily, no. I can't factor. What are you talking about? So I want to see, is there a nice way to write that so I can actually evaluate this limit? So, what is, on this picture, this is g of x plus h, yes? So what is g of x plus h minus g of x? Where is that? Oh, thank you. Good. Yes?
The area between x and x plus h.
Yes, the area between and above. So it's that little strip right there. Is that cool? G of x plus h minus g of x is this little bit here. Okay, I like it. I like it. Now, can somebody tell me, what are we going to let h do?
Get really small.
Get really small, yes. Isn't that basically a rectangle? Now, do you all agree that the top is not flat? But if I let h get really, really small, if I zoom in, and by the way, this has got to be a continuous function. If I zoom in on a function, what does it become? Flatter and flatter and flatter, yes? Straighter, so it could be like that, but as I zoom in on this function, it's going to become flat. Okay, maybe, sort of like us on the earth, yes? So there's an actual, so this is approximately, so how tall is this rectangle, especially considering I'm letting h get really small? But, and let me put some stuff in. This is t, this is f of t. How tall, I'm letting h get really small, so how tall is this rectangle? I heard here yet. F of x. You guys see that? What is f of x? Isn't that here? If I let h get really, really small, isn't the height approaching f of x? Okay, I love it. All right, I love you guys. Okay. This is so huge. You don't even know. G of x plus h minus g of x is a crazy important thing. If I can write that in a really nice way, I can figure out the stupid derivative, because that's the entire top is that. So if there's just a nice way to write that shit, I'm so much closer to done with this, yes? What is that area of that rectangle then? It's going to be the width, which is h, times the height, which is f of x, yeah. Maybe. So you're all like, okay, math boy. So let me come back. So I have g prime. I'm trying to figure out g prime. Given that g of x is the integral from a to x, f of t dt. That is so close to English, Jeff. It's amazing. Okay.
G prime of x is the limit as h goes to 0 of g of x plus h minus g of x over h, the standard way we do anything no matter what the function is. But now, how can I rewrite the top? H times f of x. And of course, what can I do? Cancel the h's out. Okay, so this is trippy. We have never seen shit like this. You have never had a function that itself was a function representing the area under a wobbly curve. We have never had that function. So how did I have to do this? We actually ended up doing the same thing we always did. When we factored polynomial stuff, we always wanted the problem to cancel, yes? So the h is the problem. It's what's making it indeterminate, correct? So the h's cancel now. We just got there in a really weird way. Now, to be really honest, we did factor the area. The area is h times f of x. So we sort of factored it. So we actually did the same thing we did before, but more geometrically than ever. So I can kill those h's. Now, I understand, and does this give a shit what as h goes to 0? So as h goes to 0, what does f of x do? It's just f of x. So what if we determined, this is underwhelming, which is unfortunate because this is tremendously huge. You have no idea. This was a monster breakthrough. And you're all like, yeah, they didn't have much going on back here. Shut up. This is what we just figured out. This is everything. We just figured out that if I have the integral of a function defined like this, its derivative is just the function evaluated at that interval. We have connected, let me see if you guys cool this. Let me see if I can get you there, okay. Let me see if you guys cool this. What's the integral of the derivative of f? What do you guys think? Alright, that's a bad idea, because we don't know that yet. Shit. What's the antiderivative? Yes. If I know that the derivative of a function is something, how do I get the antiderivative? I would have to work backwards. Then we have our little plus c, correct? So for example, if I know that the, how do you want to say this, Jeff? If I know the derivative of a function is x squared, then f of x is equal to the antiderivative of x squared, correct? And one thing we've been doing, so let me ask you this. What's the antiderivative of this? That's almost a dumb question. That's almost too easy of a question. What's the antiderivative of the derivative of g? G. You guys with me? I like it. And what did we say we're going to call the antiderivative of little f? Do it again.
Big F.
Big F. That's right. Now, there's one thing wrong with what I've just written, and I gave myself no room to correct it. So let me try this again. Leave some room after g of x. There is one thing wrong with this, because, for example, if g prime was x squared, what's the antiderivative of x squared? You can do it. Yes, x cubed over 3. Why are you wrong so far?
Plus C.
There you go, so plus c. Let me stop for a minute. I don't know if you guys are with me on this, but what we just figured out, we have just made the connection between, because what was the g function? It was the integral. And what's the big ass f function? How did we get big ass f? We took the antiderivative. So we just related the integral of something with its antiderivative. Kind of big, kind of huge. I'll make that connection even stronger in a minute, but for right now, I want to focus on what F-Talk 1 did for us. So this right here, this is fundamental theorem of calculus part 1. and I call it F top 1. Sounds like a weird radio show. F talk. It's like butter. So here's what this leads to. So if my function is this, what is g prime of x then? Can you apply the rule correctly? No. No. Yes. That's it. It's sine x. So here's the way I kind of think of this. And just to show you, the rule is if g of x is equal to a to x f of t dt, the derivative is just f evaluated at that upper thing, yes? So what's f of t here? Sine. So what's f of t evaluated at x? Sine x. So f top 1 is nowhere near as important as f top 2, but f top 2 would not exist without f top 2. So we're not going to do a ton of these. This is a derivative rule, just like the derivative of natural log of x is 1 over x. This is the derivative of an area function, of an interval function. Okay. It just, how does it work? If it's a constant to x, you just throw the x in the function that's inside and you're done. Now, let me see if I can make this make sense. So this, I've got sine. Okay. And I'm going from 3, let's see if I can make this approximately right, that'd be nice. I'm going from 3 to x, yes? Y'all with me? So listen, let me see if I can make this make sense. So this is the area from 3 to x, that's what that is. If I move a little bit in this direction, how much does this function change? Well, the way I think about that is, what if I took a little piece of tape? A little piece of tape, yes? And I put it right there. Put a little piece of tape. This tall. Didn't I just go a little step further this way? Doesn't that little piece of tape, do you all agree with me that that little piece of tape has some thickness? Does it have a lot of thickness? No. But it can't be 0 thickness or else it wouldn't be there. It would just be the thought of tape. You with me? It's sort of like I thought about getting you presents and I used the thought of tape. Okay, good. I love this analogy of a tape, and it could just be me, but if I just put a little piece of tape on it, what's the area of that tape is fundamentally just the length of that. That's how much area it's adding to it, is the length of that, which is what this says. How much would this change? It would change by how tall it is at that end. Yeah, I don't know if that helped out at all. Okay. No, screw you, Jeff. It's okay. Here, look. Circle. We do something a little more purely visual instead of graphical. What's the area of the circle? What's the area of the circle? Just an eyeball. Area is pi r squared. If I went and made r a little bit bigger, how much would the area change by? So I think of that as, if I apply a thin layer of tape to the outside of the circle, yes, it's always tape with me. Isn't that the circumference of the circle? So shouldn't the circle, if I move out just a little bit in the r direction, just make it the tiniest bit wider? How could I do that physically? Put tape around it. Wouldn't that make the circle a little bit wider? Make r a little bigger. Well, how much bigger did I just make the area? Equal to the tape length, which would be the circumference. In fact, what is the derivative of the area with respect to radius? If I go out in the direction of the radius, how do I expect the area to change? And what is 2 pi r? What is 2 pi r? It's freaking circumference. Okay, maybe. Do you guys see what I'm saying? Has anyone ever noticed that? The derivative of the area is equal to the circumference? No? What's the volume of a sphere? Does anyone remember? 4/3 pi r cubed. Write that down. What's the derivative of that with respect to r? So 4/3 pi r cubed. What's the derivative of that with respect to r? Yeah, the 3 comes down, kills that 3, yes? You guys might not remember this, but that is the surface area of the sphere. It's the same stupid idea, just put into 3D. So that's literally all we're doing here is if I have a function that goes out so far, it's like a circle that goes out this far. How do I make it a little bit? I put a little piece of tape. So how much area did I actually pick up? Whatever this height is. So in this case, this dimension acts like the height. Right? In this case, it's actually the surface of the sphere. That is the surface area for a sphere. Okay. Love you guys. And this is okay if you're not as fascinated. This is always fascinating me. The first time I saw this, I was like, holy shit, that's so cool. You guys don't have to react that way, it's okay. Don't do it now. I know you're just placating. All right. So, coming back to this, let me give you another one. Look at that. Look, that's a thing of absolute beauty. So I want to know what G prime is. And this is where students will go through insane amounts of work. And I'm great. I'm like, oh shit. Why'd you make the test so long? I didn't. I didn't. How much work is there to do the derivative of the integral?
I just changed the t's to x's.
Yeah. No, don't change the tangent t to x. That would be weird. It's inverse Zan. I picked the wrong function, but too bad. So this derivative is literally just do you see how taking the derivative of g undoes the integration? Do you see how it fundamentally just sort of takes the integral away? So it seems that derivative is the opposite of integration, which is another reason why I should understand that integration is the antiderivative. Okay, maybe. All right, let me amp this up just a little bit because you are going to see something like this, but we're not going to do this a ton. Believe it or not, this is not amped up. I can just put all kinds of shit. You just have more to write to replace every t you see, replace it with x. Ooh. But here, let's see if you guys understand what's happening here. So I want to know what G prime is. Can anyone identify the rule I've got to use? Because what is inside that side of the G function? What's actually with the inside of it? I love you guys. Sort of like the difference between the derivative of sine x. What's the derivative of sine x? Holy shit. Versus the derivative of sine of x squared. What do you have to do if you have sine of x squared? Chain rule, because what's inside the function now? X squared. So what's inside this function? X squared. Do you see it? Up here. X. What's the derivative of x? 1. That's why the answer was just this. What's inside this function now? Exactly like the difference between this and this. Do y'all agree this is a function of x? This is a function of x squared, just like this is a function of x squared, yes? So how do I do this guy's derivative? What rule has to come into play? Chain rule. How does chain rule work? How would you do sine x squared? How would you take this guy's derivative? Good, derivative of sine. So the first thing I do is I don't give a shit about x squared. Derivative of sine. Times? Now I care about x. So, what's the derivative of the integral of cosine t business? What do I do? How does that work? No. How does the integrals derivative work? I replace t with the upper limit, correct? Right? That's how the derivative works, correct? If that was this, then you guys tell me what the answer would be. What would the answer be? Cosine x cubed. You applied the rule for the derivative of an integral. You took the upper thing and you plugged it in. Okay, so what's the first step for the derivative of this? X squared cubed times chain rule. 2x. So then you get 2x cosine of x to the sixth. To be really honest, once we work with f-talk 2, I can come back to some of these and show you a very concrete way that that's what that is. We'll be able to come back and do that. So let's focus on f-talk 2 time. Oh, we got time. Ooh, yes. Okay. So I need you to understand. Do you remember the day we talked about the derivative of natural log of x? Before that day, you didn't know what it was. After that day, you knew what it was. The derivative of natural log of x is 1 over x. And then I said, oh, if I put an x squared in it, you still use the same rule. You just have to do the chain rule also, correct? That's all we're doing here. What's the derivative of the integral a to x? Oh, you just plug an x in and place a t. That's the rule. If I now put x squared in there or sine x up there, whatever, you do the same rule just like always. Times the derivative of that extra shit I put in there. Yes? Maybe? So one more. Here, let's do this. Oh yeah, I should. I'll do that next. What you got, Jeff? Let's do this. That's weird. It doesn't matter, Jeff. Just put something. You're doing it. Yay. Okay. So what is G prime? Man, I really give myself shit. What is G prime? Good. The first step is the rule for this function. How does this function work? You take what's there, you plug it in. And then, of course, what rule comes into play? Chain rule. And what's the derivative of cosine? Negative sine. Good. So you can rewrite that as negative sine x, natural log of cosine x. Yes?
So you just have to add the derivative of whatever, like cosine x,
Yeah.
squared, whatever.
And just to remind you guys, yeah, exactly, that's chain rule, right? Just to remind you guys, we did it up here. We did it here. What's the derivative of x? 1. It's just, why would we even take the effort to write it when it's just going to be a stupid 1? So remember, you always do chain rule. We just choose not to write it because it's 1 if the inside's x. If the inside's anything more than x, something's going to show up. So then students think of it as we do it then. No, we show it then. Chain rule is always there. Why would we show it if it's just times 1? The answer's 7. You forgot times 1. Shut up. 7. So I'm only going to show it if it's something more than 1. Is that cool? Okay. I like it. So here we go. Now we're going to officially, fully develop the second part. And then I think we'll take a break after this. And then I've got a handout or two. Yeah, I got two. So f-talk 1 is important because without it, f-talk 2 wouldn't exist. And also, we have a function, I need its derivative. That's how calculus works. But f-talk 1 is not used very often directly. F-talk 2 is, I've said this already, but f-talk 2 is everything. The entire rest of this class is going to depend on what this process is. No pressure on me, no pressure on you. We're going to breathe. Okay. So this is so cool to me. Okay, let's see if you guys are cool with this. Let me go back to where we started. And let me put my glasses on so I know what the hell I'm supposed to write. Blah, blah, blah. I did this right before class to make sure I remembered how to do it. It's really weird. You get to a certain point, you do all kind of shit, you prove this stuff, and then you use it forever, and then you're like, how did you prove this again? So, remind me what G of A was?
0.
Yeah, let me write it out so you guys can really see. So it's the area from A to A, which of course is 0 because it's got 0 width. So of course the area is 0. What? How would you write G of B? Might seem silly, but what's G of B? How would you write that? You can do it. Here's G of X is A to X, blah. G of A is A to A, blah. So G of B is A to B, blah. Kick ass. What'd you learn today, kids? Blah. Okay. And recall, what did we figure out earlier? We figured out, in fact, let me write it exactly the way we did earlier. Where did I put that? Shoot. Here it is. All right, good. I wrote it exactly like I wanted. Remember, recall. F of X was G of X plus C, yes? That was from f-talk 1. That was me pushing it backwards a little bit, and we got to here. Is everybody with me? We had that earlier. Okay. Could somebody help me out? What is, oh, and also remind me, what is big ass F again? How does it relate to anything over here? It's the antiderivative of that function specifically, yes? Big ass F is the antiderivative of that function there. Okay. What would F of B, big ass F of B, it would just be G of B plus C, yes? I like it. What's big ass F of A? And what was G of A?
0.
So big ass F of A is C, yes? So what is big ass F of B minus big ass F of A? Well, what's big ass F of B? It's this business. And what's big ass F of A? C. So what do you get?
G of B.
And what was G of B? Yes? All right, let me turn this around and do something. All right, let me stop for a minute. We sort of left the physical interpretation of things behind for a moment, and we have to do that with math sometimes. We have underpinnings for all this shit, but I need to work with the symbols directly. Now we can step back and go, what the hell did we just do? Before I do that, did we have to call the x-axis the x-axis? We could have called it the t-axis. We could call it the w-axis. We could have called this the y-axis and this the x-axis. Yes? And if we would have done that, you guys wouldn't think twice about it now. And we would be talking, we could have called this the x-axis. Isn't that crazy? That's what we'd be doing in the alternate universe. Are you cool then if I rewrite this as, I'm going to turn this around. I mean, I could rewrite this shit with f of w dw, f of a dA, f of, not a, but I'm sorry, f of t dt, f of s ds. The letter doesn't matter, yes? Does everybody get that? If I have the t-axis, then it's got to be dt. If I have the x-axis, it's got to be dx. They both represent the same dumb thing. If you guys draw a box and you call it xxh, and the person next to you calls it aab, are they different? If you have the same problem, no, they're exactly the same thing. You're just calling the sides different. Who gives a shit what I call the thing? But I'm going to call it x to bring it back to what we're used to. So, what have we just discovered? This means area, yes? This is asking me the area between f of x and the x-axis from A to B. That's the shit we've been working on since 5-1, yes? What is it equal to? The difference between what two things? The antiderivative evaluated at one side minus evaluated at the other side. So we just connected the area under a function from A to B to its antiderivative evaluated at B and A. That is stupid. You don't even understand. Do you guys enjoy section 5.2, where you have to figure out delta x, xi, plug it in, factor stuff out? Sum of I squared is this n times n plus 1 times 2. You guys, yes, the whole thing we did yesterday. Would you like to do a lot of those? No, I would not. I like that, and I don't want to do a ton of that. I want to do some of it, but not a ton of it. This is a shortcut. This is us going from chapter 2 to chapter 3. Limit definition derivative to shortcuts. This is the ultimate shortcut for that whole damn process. Let me immediately show you an example, and I know I'm lying a little bit because I lied earlier because it said we're going to take a break right away, but too bad. I'm going to show you an example. What is the example we did? Oh, here we go. Do you guys remember this here? This problem we did? I don't know if I still have my page somewhere. This what we get. You guys remember this problem?
Yeah.
All right, so let's write that down. I'm going to write it down for you. It was the integral, and I was going from 0 to 3, 4 plus 3x minus x squared. Does somebody have their copy of it and remember what answer we got or have written down?
For the estimate or the
Yeah, what did we get for the estimate? Start there.
16.21875.
And then I think it was 16.5 exactly, is that right?
Yeah.
Okay. So this was the best we could do by hand. That was the best we could do by hand, well, with 4 rectangles, right? And we didn't really feel like doing too many more rectangles. Okay. So when I have this, don't forget that. So without this, this is incomplete. What is the antiderivative? So if this is f, what is big ass f? What's that guy's antiderivative? Oh, that's what we did at the end there.
4x plus 3x squared over 2 minus x cubed.
Yeah, we did do that. I did more than I should have back then. It's too bad. So what this process says is that the integral from 0 to 3 of this business is equal to the antiderivative. And here's how we show, when we do integrals, here's how we show what we're going to evaluate between. We just put a little line at the end. So I think of this as this evaluated from 3 to 0. So you plug in the top number. And then you plug in the bottom number. That's just going to be 0. Is that cool? And you take the difference, yes? Because it's f of b minus f of a. As I slowly die up here. That's f talk 2. I don't have to do all the mess of xi's and delta x and plug it in and figure out sum of I cubed. What was that one? Holy shit. Yes? I could just get the antiderivative, which is relatively easy, and then plug shit in. Okay, I'll be fine. Nobody's reacting the way I think they should have. That's good. So, I think we did, what about this here? The integral of cosine x from 0 to pi over 2. Yes.
I was so lost on the other.
What? Sorry.
Like I was confused on how did you for the middle part where it's
Here?
and below that.
Here.
How did you equal this the left side to the right side?
Oh.
What happened?
Because the integral of little f is equal to the, from a to b, is equal to the antiderivative evaluated. So what we do is, we get the antiderivative, and we're going to remind ourselves we're going to put it, and then I put them in f of 3 minus f of 0.
Oh, okay.
Yeah.
Okay.
That's it. So we break it down to 2 steps. Figure out the antiderivative, figure out big ass f, and then plug the 2 limits in, subtract them. That's almost too nice to believe. So what is the antiderivative? Man, good lord. What am I drinking? Oh my god, okay. What is the antiderivative of cosine? Antiderivative. Where did cosine come from? Well, what do you take the derivative of to get cosine? No, I'm not asking for the derivative of cosine. What would you take the derivative of to get cosine? Sine, yes? And by the way, do you notice when you do integration now, it's like when you first learn how to drive a stick shift? Oh shit. Yes? Has anybody ever learned how to drive a stick shift? Yes? Yeah, you guys have to. You've done that at some point. Even if you know what the hell you're doing, you've done that at some point. So I always hear on this one, what's the derivative of cosine? What's the derivative of cosine? Negative sine. What's the integral of cosine? Sine. That sucks. Well, that's too damn bad. So when we're doing integration, we're thinking backwards. And I just have to be more mindful about that. Yes? We're so into derivatives. The whole first part of this class has been derivatives. Just drill them in your brain. Derivative, derivative. And now you go, oh shit. I'm not doing the derivative of cosine. Where did it come from? It didn't come from negative sine, it came from sine. So the antiderivative, so I'm doing this, the integral of f, I'm getting big ass f, yes? So that would be sine x. And now I gotta evaluate it between 0 and pi over 2. So you throw a pi over 2 in. So now I'm doing f evaluated at the top minus big ass f evaluated at the bottom. So this would be sine evaluated at the top minus sine evaluated at the bottom. That's how these always work. And by the way, we call these definite integrals, and if I'm missing these, we call them indefinite intervals. So an indefinite integral is just an antiderivative. A definite integral is one step more. Plug shit in. So what is the sine of pi over 2? 1. And what's the sine of 0? 0. So what's really trippy, this is very trippy if you let it be, if I get the area under cosine from 0 to pi over 2, I get frickin' 1. That's neat. Totally not expected. Okay. Unless you already knew that. Yes? Yeah, that one, we had every time, what have we done this whole semester so far? We developed derivatives, and then what did we do? Oh, we know derivatives. What's this? I know this function. What's its derivative? I know this function. What's its derivative? I know this one. Oh God. So we just kind of stepped through and went, all right, what functions do we know? What's their derivatives? Yes? So now, in this section, we created a brand new function, g of x equals a to x integral blah, 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 yes? And then we went, okay, what's its derivative? Because that's what we've been doing this whole time. So that's f-top 1 is just, in the flavor of the first part of the calculus is when you have a function, calculus says immediately, what's its derivative? Sort of like if I know how to add, I better figure out how to subtract so that I can undo it when I need to, yes? So this f-top 2 is built on f-top 1. So f-top 1, we don't really use that much. It doesn't come up very often. but it's stupid important because of the importance of f-talk2. This is everything. This, I can't stress this enough. You're gonna do this so much. So if you're like, really hate it, that was too damn bad, you're gonna be doing a lot. The rest of the semester is in. What do you do in Calc 2? What do you do? Whole first chapter is learning new ways to do this with funkier functions. Yeah, Jeff, you're selling me on it. Now I'm gonna do it. I wasn't gonna do it before. But no, it's really cool shit, but that's what you do. So let me ask you this. Could you do this problem here? What do you think to yourself to start this problem off? Yes, so we start to look at that symbol. This is why people forget that we had to make the connection between antiderivative and integrals. They are very separate, and then we discover, holy shit, they're connected. Nobody knew. And then later you're gonna forget all about it because you're gonna be so invested. But now, when I see that symbol, I can just think antiderivative is my first step. And what is the antiderivative of 1 over x? ln x. Why do you know that? Because the derivative of ln x is 1 over x. So what functions can we handle right now to find the antiderivatives of? The ones that we directly know the derivative of. Yes? If I know the derivative of f is g, then the integral of g is f. Okay. So this is equal to, now to be really, really honest, and I'm pretty sure I talked to you about this earlier this semester, in general, the integral of 1 over x is this. Do you guys remember that? Okay, real quick. Side note. Don't even write this down. Well, I don't know. Write it down. Do you all agree the derivative of natural log of x is 1 over x? Yes? What's this guy's domain? Everything except 0. So a nice way to write that is this. Yay. What's this guy's domain? X greater than 0, yes? Do you see how there's a fundamental disconnect since the two sides of that do not share the same inputs that they could use? So therefore, we understand this guy's derivative is this, and then they truly match. So when I go backwards, in general, I better put the stupid absolute values there to cover my ass. I know I've talked about that before. Specifically because I knew we were going to get to here. Now, in this case, in this very specific case, why did I really not need them? Because my inputs are both positive. They don't include any negatives between them, yes? So I can just put a 5 in and a 3 in, and that's the answer. Woohoo! You can plug it in and get a decimal, but normally I want an exact answer if it's not like how far away you live. I live natural under 5 minus natural under 3 much. Who are you? So let's take a freaking break. Let's take a break. Come back at 35 past 11:30. Let me know if you have questions. Eat them if you got them. Do. Okay, so, let me give you this. So I've got all kinds of worksheets. Yeah, this is perfect. All right, let me stop this. All right.